Hi, I'm Binja from the Ohio State University. I'm excited today to present our work, Learning Maps for Object Localization using Visual Inertial Diametry. This is joint work with my advisor, Dr. Yilmaz. Animals and humans have exceptional navigation ability in nature. For example, the desert ants can find their way by only self-motion, which is often called path integration, a mechanism to calculate the position based on animals' direction and speed of movement. Also, early research showed that animals can form a neural representation of the environment called cognitive map, which basically represents the spatial environment as a shell that can capture relationships about different locations. Our work is inspired by those biological research. Here, we describe the general motion-based localization as following sequential process. Just imagine we like to go to a place. We first start from one place and go along with a road. Then we need to make a turn when we encounter an intersection. After we made a turn, we continue to go along with the road again and repeat such process. Eventually, we will get to the destination. This process produced a sequence of nodes, turnings, and edges, which will be used as training dataset to learn the map and localize our position based on the learned map. There are plenty of literatures trying to solve localization problem, among which two types of approaches are popular. One is visual localization, where usually using 2D 3D matching or image retrieval method. Another one is probabilistic localization, which usually use Bayesian theory to estimate the position with associated uncertainty. However, those methods either need build large database, depend on appearance information of image, or conduct a complicated inference computation. Our bio-inspired localization mechanism follows the way humans navigate on the city and formulate the problem as a variable and sequence data classification problem. Overall, we define a function f which maps the input sequence to a single number under the map M. Specifically here, the map M is a topological graph with nodes and edges. We are using open source OpenStreetMap data, as you can see in the left side, which can be easily accessed and extracted from internet. We then converted our OpenStreetMap data to an undirected graph with nodes and edges as shown in the right side. Here, the capital X denotes the input motion feature sequence, which is made up of orientation and distance. For orientation information, we use local angle, which is always self-centered, and quantize the angle into discrete representation. Such representation can guarantee a unique direction and be rotation invariant. But how we can encode distance information? Here, we first identify nodes with significant orientation change, and then insert virtual nodes between two nodes, which introduces additional 180-degree turning angles. You can see the left side is original angle sequence, and the right side is new augmented angle sequence with additional distance information. The output y is defined as edge position, where each graph edge corresponds a unique location. Just suppose a map graph contains k edges, which means the output has k classes. From the figure, the highlighted edge denotes a location. Both the proposed trajectory representation contains a sequence of discrete angles, and that enable us to use a deep sequential model in the form of a recurrent neural network. The feedback architecture of recurrent neural network models the dependencies of sequential input. Here the input is the discrete motion features at a time, and output is corresponding edge ID in topological graph. This model conforms to the human navigation and localization mechanism because we're always sequentially locating our position on map based on the distance we traversed and turnings we made. Here we show that how we conduct the experiment. First, synthetic trajectory data is generated for training using graph path generation algorithm, just given a start node and destination nodes. Then we could generate many different trajectories. This table presents the basic information about the training dataset. We totally generate near 6,000 trajectories with 10 nodes, where we select 34,000 trajectories as final training data. Then, we also generate real visual inertial odometry trajectories as testing data. The reason we adopt visual inertial odometry is that it can obtain absolute scale trajectory with distance information. In this paper, we're using two open source software. One is smartphone application, which is used to collect video and inertial data. Another software where Vincent model is used to process those collected data and then generate a motion trajectory. The open source link are given here to verify our application easily. We train network using two different input data representation, the angle only and the angle plus distance, where the later case shows loss decreases more and get higher accuracy from confusion matrix, which makes sense because the angle and distance encode more information using inserted nodes. Last, we show a few real data test results. Overall, what we want to achieve here is to locate our position on a given map based on motion trajectory. Here, all the trajectories are encoded using two different methods. The highlighted edge in the map is the final prediction location. The left side trajectory is encoded by only angle. You can see in the third row, there's one false predicted location. The right side trajectory is encoded by angle and distance. You can see we inserted some virtual nodes between nodes. The prediction results are all corrected in these three examples. Even we just show a small part of the results, the whole results show that the angle plus distance performed better and also demonstrate the effectiveness of our motion-based localization using recurrent neural networks. Thank you for your listening.